We have all experienced the exact same moment. You type a question into a text box, hit enter, and watch as an eloquent, perfectly structured answer streams across the screen in real time. At first glance, it feels incredibly smart. Underneath that clean interface, there is no actual comprehension happening. A language model is simply a massive prediction machine. It takes your text, breaks it down into pieces called tokens, and mathematically guesses which token is most likely to come next. And it doesn't always pick the absolute highest probability. These models use a setting called temperature to roll a weighted digital dice, occasionally picking a lower probability option. That injected randomness is what makes the text feel creative and human, rather than rigid and robotic. Yet, for all that impressive text generation, the system is completely trapped. It can write a beautiful essay about booking a flight, but it cannot actually open a web browser and book the ticket for you. At its core, it is effectively a brilliant brain floating in a jar, completely isolated from the physical and digital world. To get from a conversational chatbot to a true AI agent, a system that can actually execute work on your behalf, requires building an entirely new architecture around that isolated brain. The foundation of this new architecture relies on the decoder, a specific section of the original transformer model created back in 2017. The models we use today are almost entirely decoders, meaning their one job is to relentlessly generate output, one piece at a time. We can upgrade this brain by giving it senses. By altering what flows in and out of the system, the exact same underlying architecture can listen to an audio file or analyze a picture of a broken circuit board, rather than just reading text. Even with sight and hearing, the model suffers from complete amnesia. It only knows what sits directly inside its context window, a strict limit on its short-term working memory. If information is not explicitly placed inside that window, the model has absolutely no idea it exists. Engineers manage this amnesia by splitting the input. You have the user prompt, which is the specific question you are asking right now. Then you have the system prompt, a hidden, persistent set of rules and behavioral guardrails. When you merge these streams together inside the context window, you define the AI's entire reality. The core skill for builders has moved past writing clever prompts. It requires context engineering, precisely controlling every single instruction, memory, and piece of data that gets fed into that window. No matter how well you engineer that context, you hit a hard limit. A model's internal knowledge freezes on the exact day its training ends. It doesn't know today's news, and it certainly does not know your company's proprietary data. We solve this by taking the AI from a closed book test to an open book exam, using a technique called Retrieval-Augmented Generation, or RAG. During retrieval, a system scans a vector database, searching thousands of documents by meaning rather than keywords, illuminating the most relevant paragraphs. Next comes augmentation. These retrieved chunks are filtered, cleaned, and neatly packaged directly into the model's context window alongside your original question. Before the AI even attempts to formulate an answer, it has the exact reference material it needs sitting right in front of it. It transforms a generic guesser into a highly specialized expert. We now have a brain with senses, short-term memory, and an open book of facts. But complex tasks require complex thought. Reasoning models are trained to use a hidden digital scratchpad, working through the logic step by step before they speak a single word. Once a model can reason, you can finally give it limbs. You provide it with tools, defined actions the AI is allowed to trigger, like calling an API to run Python code, searching the live web, or sending an email. This creates the react pattern, reason and act. The model reasons through a problem, deploys a tool, and observes the returning data. It repeats this cycle, thinking, acting, observing, updating its theory based on new evidence, until the overarching job is perfectly complete. The moment a system can independently navigate that loop to alter the digital or physical world, it ceases to be a passive chatbot. You have finally built an AI agent. Deploying these autonomous agents introduces a serious engineering challenge. Because the underlying brain still relies on that weighted dice of probability, the exact same agent might execute a task flawlessly on Monday and take a completely different, flawed approach on Tuesday. With traditional software, testing is binary. The code either works or it fails. Was the agent's tone appropriate? Did it use assigned documents? Did it execute the task safely? To manage this unpredictability, developers rely on a rigorous engineering discipline known as AI evaluations, or evals. Evals force you to define exactly what a successful interaction looks like for your specific niche. You take those subjective human priorities and convert them into concrete, measurable metrics that can be tracked across thousands of automated tests. Anyone can type a request into a text box. The future belongs to the builders who master context, retrieval, reasoning, and rigorous evaluation to construct systems that act reliably in the real world.